Space is not just an empty void. In reality, it is a constantly hostile environment flooded with high-speed radiation. Galactic cosmic rays are heavy ions fired from deep space, while solar particle events are bursts of protons coming right from our own sun. These particles are highly ionizing. When they impact atoms and molecules, they violently rip electrons right out of their orbits. If the solar system is a constant barrage of sterilizing energy, how did life survive here? On January 6, 2008, a massive gust of solar wind hit both Earth and Mars simultaneously. The European Space Agency had probes stationed in orbit around both planets to record the exact moment of the impact. This chart shows the rate of atmospheric oxygen loss for both planets during the event. The solar wind stripped away Martian oxygen 10 times faster than it did on Earth. Over billions of years, this steady atmospheric erosion turned Mars from a lush, wet world into a completely irradiated desert. Earth kept its atmosphere because it deflected the blast. Our survival depends entirely on a planetary-scale magnetic force field. To find the source of that force field, you have to go 3,400 kilometers straight down. Here, the outer core is a liquid ocean of iron alloys, superheated by the solid inner core beneath it. The intense heat makes the liquid metal rise, while the Earth's rotation, the Coriolis effect, twists it into organized, rolling convection loops. Moving conductive fluid generates electric currents. These act as a gigantic electromagnet, creating magnetic field lines that burst outward from the core. This planetary shield is a volatile, shifting geological process, powered entirely by the heat escaping from the planet's core. Those field lines extend thousands of kilometers into the vacuum of space, carving out a territory called the magnetosphere. The outward pressure of the magnetic field pushes against the inward pressure of the solar wind. Where they meet forms an intense collision boundary known as the bow shock, leading into a shield called the magnetopause. When high-speed charged particles from the sun slam into this boundary, they can't penetrate. Instead, they catch the magnetic lines and slide around the planet, harmlessly bypassing Earth. A few particles do get caught and funnel down the field lines toward the poles. They collide with gases in our upper atmosphere, bleeding off their energy as visible bands of light, the auroras. By holding back the solar wind, the magnetosphere prevents the sun from stripping away our ozone layer. It is the absolute prerequisite for biology to exist on the surface. When biological tissue is exposed to ionizing space radiation, the results are destructive. High-energy particles slice right through the tightly coiled strands of human DNA. These cosmic rays cause double-strand breaks in the DNA ladder. Unlike minor cellular wear and tear, this specific type of structural damage is exceptionally difficult for human cells to repair. Unrepaired mutations accumulate over time. For an unprotected human in space, this exposure translates directly to significantly higher rates of leukemia, lung cancer, and breast cancer. Recent studies show this radiation also damages brain cells, leading to severe cognitive impairment and accelerated neurodegeneration. Because our cellular repair mechanisms evolved under this specific magnetic cover, even a few years in open space can push human health past its sustainable limits. This creates a massive obstacle for deep space exploration. To become a multiplanetary species and reach Mars, we must leave the only natural radiation shield we have ever known. On a multi-year journey to Mars, astronauts will face constant cumulative radiation exposure, relying entirely on technology to survive the transit. Engineers are building artificial substitutes for the magnetosphere. Spacecraft walls are packed with hydrogen-rich materials like polyethylene and thick layers of water to absorb the incoming cosmic rays. Researchers are also developing radioprotective pharmaceuticals. These drugs are designed to help mitigate oxidative cellular damage from the inside out. Whether through hydrogen-rich polymers or water-shielded habitats, moving beyond Earth requires us to carry a fragment of that subterranean protection into the void.